Hi everyone, this is Chapter 9 of AP Statistics. We are going to have 3 sections in this chapter. Just like the last chapter where the first section was all about the basics and then the second and third sections were about the logistics of how you actually do the thing. That's how we're doing here. So this chapter is all about significance tests, and this first section is all about the basics. So after this first section, you're going to do a lot of things, but the main ones, you're going to be able to state correct hypotheses. You're going to be able to interpret p-values, figure out what those are. You're going to be able to describe different types of errors, among other things. So let's dive right in. The biggest differences between this last chapter, Chapter 8 and Chapter 9, in Chapter 8, we were trying to estimate a population parameter, right? We were creating a confidence interval. It gave us a range of possible values for some unknown population parameter. We focused on population means and population proportions, but you could do a confidence interval for anything about a population. You could do it for medians, standard deviations, IQRs, etc. Now, this chapter is about significance tests. We are going to now, instead of estimate, we are going to assess the evidence provided by data about some claim concerning a population. So we're either going to reject or fail to reject this claim. So either yes, we think it's true, or no, we do not think it is true. It's going to get a little bit more complicated than that, but that is the basics. So think about this. A recent study on the relative age, effect, and career success, evidence from corporate CEOs suggests that people born in June and July are underrepresented in the population of corporate CEOs. This is consistent with the relative age effect due to school admissions grouping together children with age differences up to 1 year, with children born in June and July disadvantaged throughout life by being younger than their classmates born in other months. I myself was born in July and was always one of the youngest ones in my class. I was only 17 when I graduated high school. In their sample of 375 corporate CEOs, only 45, which is 12%, were born in June and July. Now, based on this sample, is it convincing evidence that the true proportion, P, of all corporate CEOs born in June and July is smaller than 2/12? Where do we get 2/12? Well, if it's evenly distributed, then 1/12 for each month, so 2/12 for June and July. So give 2 possible explanations for why the sample proportion was below 2/12. Why could that be? Well, either the assumed proportion, 1/6, 2/12, right, is correct, and the statistic, which was 12%, differs because of a random chance, or, more likely, the assumed proportion is incorrect, and the statistic is actually more consistent with the true population proportion, meaning that kids born in June and July are, in fact, disadvantaged in the workplace. Okay? We can do a simulation. Okay, we can do a simulation. And when we do a simulation, we find that it is actually very unlikely to get a sample proportion as low as 0.12 by chance alone. That means that there is going to be convincing evidence that people born in June and July are underrepresented in the population of CEOs. You can use a sampling distribution of p-hat in order to calculate this probability, or you could have done a confidence interval, for p-hat to estimate the true probability. So, there is a quick little teaser to help us see what this chapter is really about. Significance tests. So, like a confidence interval, we're seeking to infer something about the population. But a significance test is a procedure for comparing observed data against some claim, right? Something believed to be true about the population parameter. So, here's the basic idea of this whole chapter. If an outcome would rarely happen, if that claim were actually true, that's going to be good evidence that the claim is not true. If it's not likely to occur, then it's probably not true if we get that from our sample. Now, unlike in science, statistics writes hypotheses when evaluating a claim, right? Our hypothesis is kind of what we are saying we think is true. Now, the 2 hypotheses are the null hypothesis and the alternative hypothesis. The null hypothesis is represented by an H with a subscript 0. We will sometimes either call that H sub 0 or H sub O. Please don't call it ho. Thank you. Now, the null hypothesis is going to be the claim that we are testing. In our class, it is always going to be of an equality, something with an equal sign. So from our CEO example, we were claiming that everything was equal, right? We thought it was all the same, so the true proportion is 1/6, right? 2/12. Now, the alternative hypothesis, which is H sub A, this is the claim that we're checking for evidence for. Okay, so the difference between the claim we are testing and the claim that we're checking evidence for. So we thought that it was untrue, right? We thought that they were underrepresented, that they were disadvantaged, meaning the proportion of people born in June and July was actually less than 1/6. So these hypotheses have to be written in tandem. You have to have a null and an alternative when you write your hypotheses. So let's do some examples. We want to both define the parameter of interest and also state the appropriate hypotheses. First example, Mike is an avid golfer who would like to improve his play. A friend suggests getting new clubs and lets Mike try out his 7-iron. Based on years of experience, Mike has established that the mean distance that balls travel when hit with his old 7-iron is 175 yards with a standard deviation of 15 yards. He is hoping that his new club will make his shots with a 7-iron more consistent, aka less variable. So he goes to the driving range and hits 50 shots with the new 7-iron. Alright, so what is our parameter of interest and what is our hypotheses? What are our hypotheses? Now, since Mike is interested in being more consistent, the parameter of interest here is going to be the standard deviation of distance he hits the ball when using his new 7-iron. So before, right, my null, we claim that our standard deviation is 15, but he wants to see if he's more consistent. So we want to see if the new standard deviation is actually less than 15, right? A smaller standard deviation means that he's more precise or consistent. Now, the second example, at the Hawaii Pineapple Company, managers are interested in the sizes of pineapples grown in the company's fields. Last year, the mean weight of pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing seasons. Managers wonder if this change will affect the mean weight of pineapples grown in the field this year. Now, notice how it didn't say one way or another if they think it's going to increase the weight of the pineapples or if it's going to decrease. We just want to know if it's going to affect it, if there will be change. So the parameter of interest is the mean weight, mu, of all pineapples grown in the field this year. Now, like I said, because the managers wonder whether the mean weight is going to differ, the alternative hypothesis is what we call two-sided. So either the mean is going to be less than 31 or greater than 31. Just saying like there was a change. So for simplicity, we're going to write this as the mean does not equal 31. As in, it's different than what they are claiming. The null hypothesis says there is no difference after it was changed. So our null hypothesis, H sub 0, is going to be that mu, my population mean, is equal to 31. And that my alternative hypothesis, H sub A, is going to be that the mu is not 31. Now, we kind of touched on it in this example, but there's different types of alternative hypotheses. You can have a one-sided alternative hypothesis. This is where you think, this is a typo right here. This should say parameter. Either the parameter is greater than the value or the parameter is less than the value. And the two-sided hypothesis is just that the parameter is different than the value. So these statistics should say parameter. So if the question says, we strongly suspect that a new blood pressure medicine decreases blood pressure, if the null hypothesis is that the mu is 0, which would be the correct alternative? The correct alternative would be that it is less than, because we say that it decreases. So you have to be pretty good at reading the problem and understanding from the context what your hypotheses should be. In our next video, we're going to talk about p-value and what the heck that is and how you would interpret it.